Hello again, Year 12. Sort of following on from the previous video about oxidation numbers, oxidants and reductants. So just to recap, just make sure you've understood. Oh, hold on. If you don't know about oxidation numbers, you're watching this video too early. You need to go watch the assigning oxidation numbers video so that you can assign oxidation numbers correctly. Then you're ready for identifying oxidants and reductants. I'm going to do that. Try not to say that again. So oxidation, increase in oxidation number. Reduction, decrease. So they are going to be the opposites of each other. I see my cat has appeared in the background. One of two. The identification of oxidation numbers means that you can then spot whether something has changed by increasing or decreasing in its oxidation number during a reaction. Now, there are two terms that get confused: oxidized and oxidant, reduced and reductant, because they are very much not the same thing. Oxidized is a statement about whether the oxidation number has gone up or down, or any of the other three definitions of oxidation. An oxidant is a chemical that causes oxidation, so it's not the same thing. So here's a working definition of oxidant. An oxidant will oxidize something else. So that something else could be, it could be an element, it could be a compound, it could be an ion. So the word something else is a sort of cover-all term. An oxidant will oxidize something else and be reduced itself. So that's what happens to an oxidant. Anything that is reduced is going to be the oxidant. Reductant, complete reverse, because they are like two sides of the same coin. They are the reverse of each other. So if you're going to, and I do recommend you pause the video and write stuff down about this, rewind the video if you need to. The definition of a reductant you need to write down now. It's just the complete opposite. Will reduce something else and be oxidized itself. That's it. I'm going to get the board ready for some examples. I'll see you in a moment. So here we are with some examples, just momentarily. Just a alternative recap of what we've just said before. If something is reduced, so you look at the oxidation number of something and its oxidation number has gone down, it has to have been an oxidant. And you can turn that round the other way and go, if something has been oxidized, it has been a reductant. That's the two words, try not to get them confused, because they are the reverse of each other. We'll do it with a couple of examples. Here's a very common reaction, even from probably year 9 for most people. So chlorine displacing iodide ions out of solution, displacement reaction. Look at the oxidation numbers. Here iodine is -1, here iodine is 0. So that is oxidation. Chlorine is 0, chlorine there is -1, that is reduction. And in the manner of this up here, if something has been reduced, it has been the oxidant. Chlorine is therefore, by virtue of chlorine being reduced, it has to have been the oxidant in the reaction, and therefore that's the reductant. So this is what we're trying to do. We're trying to identify the oxidant and the reduction. Sorry, that's wrong. The reductant. We're trying to identify the oxidant and reductant by looking at whether things have been oxidized or reduced, and never confuse the two terms. Let's try. Another example. Now this is an important example for two reasons. One, it's a really common reaction in A-level chemistry. It's used in titrations, it's used to find the amount of iodine. Iodine is also used to give you access to the amounts of lots of other substances, so this is often final point of a sequenced set of instructions or procedural instructions, and it gives you this multi-mark question where you work back to find out some kind of analysis situation, and there's a book of mine coming out about that very soon. But this is not about all of that. This is just about the oxidation number change. The other point is that this substance here, the sulfur, is one of those examples where it's got a fractional oxidation number. Now, I said to you in the previous video, there's no such thing as a fractional oxidation number. It's just that that's the mean value or the average value. So when you look at these, the oxidation number here is +2, here it's +2.5, meaning some of the sulfurs are 3, some of the sulfurs are 2, well, half and half. So that is oxidation. And here 0 to -1, so that is a reduction. So when you put that together, if it's been reduced, it's an oxidant. So the iodine is the oxidant. It's caused oxidation of something else, and therefore this must be reductant. Now, as for the names of these, this is thiosulfate. This here, interesting name of substance, that there is called tetrathionate. Helpful to remember, but not necessary for this video. But I'll put it there for those people who like these things. And if you're year 13 using these to revise with, then you will need to know the name of that. So that product ion there is called tetrathionate. So here we have these two examples. They are ionic equations, because often you find this as ionic equations. It gets rid of all the spectator clutter and focuses in on what's changing in oxidation number. And then we'll clean the board up and do a little bit more. See you in a moment. So now I want you to have a go with these two. So steps are: 1, identify oxidation numbers of whichever things you need to identify, but really you're focusing in on the ones that are changing. In the top one, they're all changing. In this one, not so. The balancing numbers are kind of a distraction for this task of identifying oxidant and reductant. Oh, I've done it again. And because all you're looking at is what are the oxidation numbers, not anything else about the balancing. So you don't need to fuss about the 4, the 3 and the 2 in the top one, for instance. Identify changes in oxidation number, then name the oxidant, name the reductant. And in this one, it isn't an element that is the oxidant, or it is actually the name of one of those two substances. So one of those, the whole thing, FeCl3, will either be the oxidant or the reductant, not focusing in on what's changed. Oh, my other cat's made an appearance. There we are. There we are. That's Geddy. So I'm going to get you to pause the video and have a go doing those, and when I come back after the edit, we'll have the answers on the board ready for you. See you in a moment. So here's the answers. You just need to look at the oxidation number changes. Fe has gone up from 0 to +3, that makes it oxidation. Oxygen has gone down to -2 from being an element at 0, it's reduction. So therefore, oxidant, oxygen, reductant, Fe, because the Fe has been oxidised, so it must be the reductant, and vice versa for the oxygen. Same idea here. I just identify the changes. Fe3 plus to Fe2 ions in those substances will be a reduction from +3 to +2 in oxidation number. The sulfur in the hydrogen sulfide has gone up from -2 to 0, so it's been oxidised, and therefore you just flip them. Oxidised becomes the reductant, hydrogen sulfide, and therefore the FeCl3, which is reduced, has become the oxidant. We'll just do one more example and then we'll move on. I'll see you in a moment for that example. So a slightly more complex example, not massively more more complicated. You just need to identify what's been oxidised, what's been reduced, and then you can name the oxidant and the reductant. That's it. You need to pause the video and have a go, and I'll see you after you've had a go. Thank you. So there's the answer. Reductant and oxidant. Oxidation number changes are there, which obviously you needed to have identified and got the numbers correct in order to show that the nitrogen within some of the nitrate has been reduced to NO2, but obviously not all of it, because some of it has stayed there, and that's the slightly confusing bit, is following what has changed and what has not changed. We've got a related thing just to quickly discuss called disproportionation, but I need to get that on the board so that I can explain it to you. So I'll see you in just a moment. Disproportionation feeds into my love of long words. It's the longest normal word I found in chemistry that isn't a chemical name. FeCl2 turning into FeCl3 and Fe, which is what it does if you sit it around. And that equation with those oxidation number changes fits the definition of disproportionation. If you look at the Fe in FeCl2, it has a +2 oxidation number in either of those there. So in going to FeCl3, there's oxidation, goes up by 1. In going to Fe, it drops. So here and there, you've got oxidation and reduction. So the iron has been both oxidised and reduced in the same equation. Definition of disproportionation. Definition, you need to write this down because you need to remember it. Definition of disproportionation is an element is both oxidised and reduced in a balanced chemical equation. That's it. I'm going to clean the board, put 2 further examples on for you to prove that they're disproportionation. Say a couple of things and then we're done. See you in a moment. So here are 2 reactions. They are both disproportionations. So we're not asking you to see whether they are or not. They are both disproportionations. All I want you to do is identify the oxidation number changes to prove that they are disproportionations. So you need to do that, and then if you pause the video to do that, I'll see you after you've done them and with the results and the answers, or whatever you want to call them. See you in a moment. So here's the answers. Iodine in the top one has been both oxidised and reduced, therefore it fits the definition of disproportionation. The iodine has been disproportionated, we could say. And those are the oxidation number changes there. Here it's the element chlorine that has been both oxidised and reduced. There it is, going up to 7 and down to -1. So the chlorine has been disproportionated in this reaction. Now that does bring to mind a thing about all redox reactions. This is not just disproportionation, this is any of the examples of redox that you could come across. There has to be, for it to fit the definition of a balanced equation, as much oxidation as there is reduction. Now what that means is if you've got an increase of +6 going on in the reaction for some element being oxidised, there has to be a -6 amount of reduction to match it. Otherwise it's not balanced by definition of balancing. But that's not for this video, that is for a different video on another day. So there we are. Oxidants and reductants. There are some follow-up questions for you to have a go at, and the answers will be shortly following them once I've typed them up. And I'll see you soon. Thank you very much for watching. Goodbye.